All right, so moderation that they were talking about in the 2-minute passion-driven stats video is tested in categorical designs with Anova. So the interaction term is a test for moderation, but the Anova, and it's a special Anova called a factorial Anova, provides a few other effects. So I have to supplement their video with another video that teaches us in depth about the Anova and hopefully clears up some of the questions we've been having in class about how the Anova works. So the Anova, the test itself, is all about parsing variance. That means there are a lot of factors that impact data. We're trying to determine how much each of those factors cause variation in our data. Variation, changes, differences, how much our factors, good and bad, impact our data. So when you're thinking about what factors impact a piece of data, I like to look in at one number in a complex data set. So in this data set, we can see it involves two independent variables, personality, which is introversion and extroversion. And it also looks at watching different movies, Billy Madison, Happy Gilmore, Little Nicky. And so that's another independent variable, what movie you watched, and the dependent variable is how funny you found those movies. So if we look at that number 5, what causes data point to be a number 5? And a lot of people say, I don't know, I never thought about that. Yeah, think about it. That number is a number 5 in part because participant E watched Billy Madison, because participant E is an extrovert, because special things may happen when extroverts watch Billy Madison, because participant E just has a high level of humor in general. We can see that in the data set. They have the highest humor scores, or just random crap that we don't know where it's coming from. This is what Anova does. It parses your data into these different effects, like what percentage of change in the entire data set was driven by your independent variable personality, what percentage of change or variation in the data set was driven by watching these 3 different movies, what percentage of the variation was caused by the interaction between personality and watching these specific movies, what percentage of the variation was driven by that person's humor, their personality, their individual differences, and what percentage of this variation is caused by crap that we don't know where it came from. That's analysis of variance, parsing those components into a specific component of variance. Now, Anova is analysis of variance, and I just said this, it calculates variance for a whole bunch of different types of components. Now, be aware that the statistical packages call variance mean squared. Now, what is variance? That's a good question. Mathematically, it's sum squares divided by degrees of freedom. But conceptually, it just tells us in a set of numbers, how much do these numbers differ from each other? That's all variance is. Remember, variance is the average squared deviation from the mean. That we used when we were calculating standard deviation. Now we can get more complicated with it, and we can look at variance that's due to personality. Like, this is just saying that personality caused our data to differ by this much, a variance amount, right? Variance is a number, so this much would be whatever the variance number is. We call this the foundation of our main effective personality. In this example that we just used, there's going to be variance due to the movie type. Those 3 different movies differ in funniness, right? So these movies are going to cause data to differ by a variance amount or by this much. Variance has a number, so you'll be able to say, oh, you know, when we have that number, we'll be able to say, oh, movies cause data in this data set to differ by a variance amount. The variance is a number. This is our main effective personality. There's also variance due to personality and movie working together. We call this an interaction. There are special things that can happen when you put personality types in movies together. Some personality types might like Little Nicky better, right? Like introverts might really respond to Little Nicky because they feel like maybe that's them, or extroverts may really respond to Billy Madison because they feel like that's more relatable to them. Who knows? But special effects can happen when you put 2 variables together. Well, there is the variance that's caused by this interaction. That's another definition. And a variance, and this is our interaction term. There's also variance that's due to error. Well, what's that mean? That's variance that we know exists. We have no idea why. It's due to crap that we didn't think about or control. So Anova is just about parsing a complex data set into these various variance components. All right, degrees of freedom is super complicated. and you won't understand it unless we do a calculation of Anova by hand, which I do plan to work out in class. But I think it's we've already seen it. It's that Bessel's correction, that n-1. That was for an entire data set. So the total degrees of freedom is essentially Bessel's correction. So the sum squares, or the variance for a total data set, is just, number of observations minus 1. That's Bessel's correction. That gets us closer to a population value. That's why we use these degrees of freedom, right? But we've seen it once. But let's talk about it. The main effect for personality is the number of conditions minus 1. There are 2 conditions minus 1, so there's 1 degree of freedom. For the main effect of age, there are 3 conditions minus 1, so there's 2 degrees of freedom. For the interaction, it's the degrees of freedom of the main effect times the degrees of freedom of the other main effect. So for this example, it'd be 2 times 1 is 2. For the total data set, and this is the one we've already learned, it's the number of observations minus 1. For the individual difference effects, or the subject's effects, and within subject's design, it's the number of participants minus 1. Error equals total minus all of other effects that you have, right? Error is just, we don't know. But essentially, at the end of the day, degrees of freedom is super complicated. It doesn't matter that much. It's just tradition that we put the degrees of freedom with our statistics. I can explain why in class, and I do plan to do that a little bit. Now, the F ratio is where we figure out our p-value from. But essentially, the F ratio is just the variance of your effect of interest, your main effects, or your interaction, just individually, divided by the variance that's due to error. Now, for example, if we find an F ratio of 2, what's that telling us? Well, look at the equation. That's telling us that our variance of the effect is 2 times the size of our variance of error, right? That's all we're learning here. Now, I want to talk about the case where your F ratio equals 1. That means that the variance of your effect is equal to the variance of error. This is not good. In science, we want error to be minimized. If the variance of your effect is equal to the variance of your error in your study, how do we know that the variance of your effect matters or isn't due to error itself, right? You really got to think about that, okay? If the science is supposed to minimize error, it's kind of not scientific to say that you found an effect that causes the same amount of variance that error causes, right? In order for there to be an effect, it has to have a much greater effect than the error causes. So the F ratio is weird. I acknowledge it. But if you look at it as a fraction, it's like, like if my F was 5, the variance that's due to my effect, whether it's a main effect or interaction, it doesn't matter, is 5 times that of error, suggesting that error is that much smaller than the size of our effect, that we believe our effect is real. But if our F ratio is 1, we're saying that the variance that's due to error is equal to the variance that's due to our effect. Guess what? Our effect is the same size as our error. Error is supposed to be minimized. We haven't minimized error here, and that's the logic of the test. So now let's just get into the bare bones. What do you need to know to do a factorial ANOVA? When do you use a factorial ANOVA? Well, you use a factorial ANOVA when you have 2 categorical independent variables and 1 continuous dependent variable. So you have, for example, in the practice test, we had 2 categorical variables, age, which you're like, wait, age is continuous. Not when the ages that they were measured at were 6, 13, and 20. So that's a categorical variable. And personality, which was introversion and extroversion. So that is 2 categorical variables, and our dependent variable was how funny Sandler movies were. And if we remember, when we looked at that data, we saw that Sandler movies got less funny the older you got. But that's just a fun callback to the previous lecture. But we use an ANOVA when we have 2 categorical independent variables and 1 continuous dependent variable. The notation that we use to describe these ANOVAs is quite confusing to students. They mess it up all the time. So I'm going to make it very clear. So a 5 by 5 ANOVA does not mean there are 5 independent variables or 25 independent variables. No, there are 2 numbers that indicates there are 2 independent variables. A 10 by 10 by 10 ANOVA indicates that there are 3 independent variables. A 10 by 4 ANOVA indicates that there are 2 independent variables because there are 2 numbers. The number of numbers tells you the number of independent variables you have. Now, in that first example, that 5 by 5 experiment, in independent variable 1, there are 5 conditions. In independent variable 2, there are also 5 conditions for a total of 25 total conditions. In the second experiment, there are 10 conditions for independent variable 1, 10 conditions for independent variable 2, and 10 conditions for independent variable 3 for a total of 1,000 conditions. And in the last experiment, there are 2 independent variables, but the first independent variable has 10 conditions, and the second independent variable has 4 conditions. Okay, so a blank by blank ANOVA is saying there are 2 independent variables. A 20 by 20 ANOVA, there are 2 independent variables, 20 conditions in independent variable 1, 20 conditions in independent variable 2. All right, you got to learn that, so memorize that. Now, the between subjects ANOVA means that participants are only assigned to one of all the conditions. In that experiment, participants would only be assigned to one of 25 conditions. In the next one, so within subjects ANOVA, that means that participants are assigned to every condition. They participate in every condition. And in this case, they'd participate in 1,000 different conditions. Now, finally, in this 10 by 4 mixed subjects ANOVA, that means one of the independent variables is a between subjects variable. So they're only assigned to, let's say, one of the 10 conditions, but they complete all 4 of the other conditions. That would be a within subjects variable. So it's when you have one independent variable that's a between variable and one that's a within, we call it a mixed ANOVA or a mixed subjects ANOVA. Don't lose that notation. So in this example right here, we have a 2 personality, introversion, extroversion by 3 age, 6, 13, and 20 mixed subjects ANOVA, because that's how I set up the data set. If you remember that data set, participants, how funny they thought Sandler movies was measured when they were 6, when they were 13, when they were 20. So, that's the dependent variable, how funny they found the movies. But they were measured, that was measured 3 times at 6, 13, and 20. Age is a within subjects variable. Personality, you can only be introvert or extrovert, so that's a between subjects variable. So together it's a 2 by 3 mixed subjects ANOVA. It's also really important to understand that whenever you run a blank by blank ANOVA, you're testing 3 null hypotheses at the same time. So when you get to the Jamovi, there's a lot today. So you have to approach, each ANOVA has 3 separate tests. I'm going to describe those 3 tests, but they have 3 sets of descriptive statistics, 3 p-values, 3 graphs, 3 effect sizes, and you know what though, with the interpretation, you put it all together, you have 1 interpretation, but you have like 3 of everything. So it's 3 times the pain, and just get prepared for that. Now one of the effects that we'll examine is called a main effect. What's a main effect? This would be the effect of age on Sandler funniness, right? Just on how funny those movies are as determined by age, while ignoring personality. So main effects ignore the other independent variables. So this is basically, in this example, that's from our practice test, it's basically a one-way ANOVA. The null hypothesis is that the population means are not the same, and there are 3 or more means, so it's in that one-way ANOVA kind of effect. If we find a significant difference on this effect, we'd have to run a post-hoc. Now, the second effect is the effect of personality on Sandler funniness, while ignoring the effect of age. So there's only 2 personalities in this study, introversion and extroversion. This is basically a t-test, so the null hypothesis is that the population mean difference is 0. But essentially, a main effect is just either a one-way ANOVA or a t-test. It's in a complicated design, but you ignore the other independent variables. An interaction is really not that difficult. Folks struggle with it, but you can think about it this way. Does something special happen when you put 2 variables together? Right? If it does, then there's an interaction. It's kind of like a reaction. Now, essentially the null hypothesis is that the population slopes are the same, and you will see this in the video. It will make more sense in a second. However, I just wanted you to know that there are 3 effects you're testing. A main effect of variable 1, a main effect of variable 2, and the interaction of independent variable 1 and 2 together. Now, post-hoc tests exist in an Anova. You run them only if you have, and for main effects, you only run them if you have a 3-level independent variable and it's significant. If you have a 2-level independent variable that's significant, you know which 2 means are different in the population. There's only 2 population means that can be different. So if you have a main effect with 3 or more levels that's significant, you run a post-hoc test. For the interaction, you can run all sorts of cell mean comparisons. So when I say a cell mean, I'm talking about the different combinations of the 2x3 design. So in this Sandler study, I'm looking at funniness of Sandler at 6 in introverts. Does that differ from the funniness of Sandler at 6 for extroverts? That's one possible post-hoc comparison we could make, comparing different cell means. Now, if cell means don't make sense, they'll make sense in a second when we go through the descriptives. But ultimately, you run post-hocs after a significant interaction or after a significant main effect with 3 or more levels. Now let's go ahead and run some practice Anovas to see how this all works out. Today, I'm going to not do descriptives until the very end of the video because they're actually kind of complicated. So first things first, we're going to run a 2x2 Anova. That 2x2, there's 2 numbers, so that means there's 2 independent variables. The first one is personality type. That has 2 levels, right? So that's where the 2 comes from. By 2, serious disease, that also has 2 levels on Beck depression inventory scores. So that's a 2x2 between subjects Anova. How do I do that? I'm leaving the descriptives out, but how do I do that? Analyze Anova. My dependent variable, Beck depression inventory scores. Personality and serious disease are my independent variables. I want my partial eta squared. Okay, we get all of our p-values and our partial eta squared. What do we see here? Well, remember that we are making 3 different hypotheses, 3 different conclusions. My main effect of personality is not significant. My partial eta squared is between small and medium, because remember, it's 1%, 6%, and 14%. All right, I know nothing. Serious disease, p is greater than 0.05. I know that those, I don't know what direction it is yet, but I know that those with a serious disease and those without a serious disease have different depression scores, and that's a large effect. We'll let the figures will tell us what's going on there. So I have the population means are different, and it's a large difference. The interaction was non-significant. Okay, so what that means is nothing special happens when you put personality and disease seriousness together and predicting Beck depression inventory scores. So our next step is to click in the estimated marginal means box and get a picture for our main effective personality, which was non-significant. We can see here, if we look at it, if it was significant, it would suggest that introverts were more depressed than extroverts. But look at those error bars. Let me change them to standard error, even though I may like the confidence intervals. And then we're looking at this, still we make the same conclusion. There's too much error, particularly in that extrovert group. Let's make our graph for our main effective serious disease, which was significant. This is one we're really interested in. And we want to look at this. Those without a serious disease reported being more depressed than those with a serious disease, which is not what I would have expected. If I did find this, it tells me something about processing death. Now, I made the data up, so we got to understand that. But this would be a surprising finding, and it might lead to an interesting area of research. I want to make a graph for the interaction that was also not significant, all right? I'm dragging in both terms. You can drag them in one at a time. And what you'll see here, when I said that the interaction was a test of slopes, it's saying, is this slope different from this slope at the population? Well, our p was greater than 0.05, so no. But if it was significantly different and we were asked to interpret this interaction, what would we say? We'd say for those with a serious disease, one's personality type mattered. Those that were extroverted were more depressed than those that were introverted. Those without a serious disease, their personality type did not impact depression scores. All right. Now I'm going to add a 4th graph. And what I'm going to do this time is add serious disease first and personality second. you don't need to add this fourth graph. I just want to show you that these two graphs have the same data, but one might be easier to read than the other. So if I look at the second graph, it's pointing out the same data. But to me, it looks more in line with our hypothesis that the two slopes were the same. So this one might be more appropriate for this p-value. But what's it saying? It's saying for introverts, serious disease looks to reduce their BDI scores. And for extroverts, right, having a serious disease appears to reduce their BDI scores even more. So for our next ANOVA, we're going to examine two independent variables. The first one being personality type. That's a between subjects variable. Has two levels, introvert, extrovert. So it's a 2 by, I'm going to look at semester timing, beginning of the semester, end of the semester. That's a within subjects variable. It's a 2 by 2 ANOVA on happiness. So I'm going to skip the descriptives till the end and the write-up till the end. So I'm going to click Analyze, ANOVA. I have to click Repeated Measures. Even though it's within, you still use the Repeated Measures dialog. So we use ANOVA for between, Repeated Measures for within. Click that. My repeated measure is semester, beginning, end. All right. And I have a between subjects factor that was personality right here. And I'm going to go ahead and start looking at some outputs here. We have various p-values. Was there a main effect of semester? There was a significant main effect of semester. Was there a significant interaction of personality and semester? Yes. Was there a significant main effect of personality? Yes. So we have 3 significant effects. That's awesome. So I want to look at my partial eta squareds, get my effect sizes. Large effect, large effect, large effect. They're all large effects, so that's good as well. I want to go ahead and look at my graphs. So the first graph is the main effect of semester. My second graph is the main effect of personality. My third graph is the interaction of personality and semester. And my fourth graph is the same interaction of personality and semester. I just put personality in first and semester in second. And now I get all my graphs. So for the main effect of semester, participants were happier at the beginning than they were at the end. For the main effect of personality, extroverts were happier than introverts. For the interaction, I gotta kind of like look at these two graphs and to make sense of them. So it looks like for extroverts, as the semester went from the beginning to the end, their happiness dropped more than introvert happiness did. So that's what I'm seeing here. For introverts, happiness dropped less than it did for extroverts as we went from the beginning to the end of the semester. When I look at it the other way, it says at the end of the semester, I like this second way better. This one makes more sense. At the end of the semester, extroverts and introverts did not differ in terms of their happiness, but at the beginning of the semester, extroverts were happier than introverts. So happier, sadder, equal happiness, essentially. So I now have three significant main effects. Okay, well, 2 significant main effects and a significant interaction. A main effect is just looking at personality, ignoring semester, looking at semester, ignoring personality, and the interaction is looking at them both together, seeing if any special magic happens. It did. So let's look at our post-hocs. Would we run a post-hoc for semester? There's only 2 levels. No. We run a post-hoc for personality. There's only 2 levels. No. Would I run these post-hocs for the interaction? I found a significant interaction, so I would. Let's see what this is doing for us. First thing I'm going to point out, you won't be able to get a Cohen's d here. If you want to get a Cohen's d for this, you know how already. You just got to run the paired samples t-test for the comparisons you want to make. Now, let's talk about what comparisons I want to make. I really just want to make 2. I want to see if extroverts and introverts at the end of the semester had this like a non-significant difference. I'm predicting a non-significant difference at the end of the semester between extroverts and introverts. And at the beginning of the semester, I'm predicting a difference between extroverts and introverts at the beginning of the semester. So that's only two t-tests I want to conduct. So extroverts at the beginning of the semester to introverts at the beginning of the semester. It's the first line here. I'm predicting a significant difference, and it was significantly different. The other comparison I wanted to make was at the end of the semester, extroverts at the end, introverts also at the end. That's this line right here, non-significant. So essentially, those are the only two post-hocs that I would report in my data. Those are the only two post-hocs that I'm actually interested in. Now, you could argue and do other comparisons, right? How you deal with the post-hoc output is a little bit up to you. You could be like, oh, I also want to compare, and extroverts at the beginning were different than extroverts at the end of the semester. Introverts at the beginning were different than introverts at the end, right? You can add whatever you want here. But for me, I like to keep it simple. I like to explain the difference in slopes. And so if this is a significant difference and this isn't, that explains my slope difference. So here is another data set. It's a 2x2 completely within subjects Anova. In this data, it's taken from my research. Nurses provided empathy ratings for a white male patient, for a black male patient, for a white female patient, for a black female patient. There are two independent variables: race, 2 levels, white and black; gender, 2 levels, male and female, of these patients, right? The dependent variable is empathy. We want to analyze this data with a 2x2 Anova. So we click Anova, we click repeated measures Anova. My repeated measure factor number 1 is race, white versus black. My repeated measure factor number 2 is gender, male, enter, female, enter. All right, now we have that all completed, and you'll look down here, it says repeated measure cells. And it says, okay, put the white male cell here, the white female cell here, the black male cell here, and the black female cell next. What you're probably noticing is that it's giving us our various F statistics and p-values. So now I click partial eta squared. And what do we see when we're looking at this data? Like, it's a within subjects design. So we see that, okay, the F statistic for the race main effect is about 3. So that means the variance caused by race is 3 times the variance caused by error, but it's non-significant. It's large. We still know nothing. We have the same thing for the gender main effect. The main effect of gender is about 1.45 the size of error. The p-value is non-significant, and it's a large effect, but we still know nothing. And again, we look at this 2.21 for the interaction. The interaction effect was greater than twice the effect of error, but that is not significant. We know nothing. You're like, oh, why do we have these effects that are greater than 2 and they're non-significant? We only have 5 observations in the data set, so it's less likely to find significance because of that. What else do we need? Well, we're going to need our graphs. So the main effect of race graph, let's add another graph. The main effect of gender graph, let's add another graph. The race and gender interaction graph, let's add a second interaction graph just so we can choose what, like, it'll help us interpret the data, right? So we've been doing that all along. We add our second race and gender graph just to see if we can understand the data better. When we look at this, the main effect of race shows more empathy for white patients than black patients, more empathy for female patients than male patients, the main effect of gender. Now, the first way we're looking at the interaction shows that for female patients, it appears that there's a slight reduction, but not really, right? We know it's non-significant in empathy for black patients and white patients. That reduction in empathy for black patients compared to white patients appears to be greater for men. if we look at it the other way, we're like, oh, for white patients, there's no difference in empathy across gender. But for black patients, it appears that women patients engender more empathy than male patients. Now, it wasn't significant, but you can see why making the two plots allows us to better understand that interaction. If it was significant, right, these two slopes are different. Now, post-hoc tests, we wouldn't run one for gender. We wouldn't run one for race. We wouldn't even run one for the interaction because it was non-significant. But if we did, right, all it does is it compares every single possible cell mean. And we'd have to choose which ones we want to compare. But ultimately, this post-hoc test compares, the white male empathy to white female empathy. White male empathy to black male empathy, white male empathy to black female empathy. It does all the comparisons. So there's no more, you don't have to guess about, is this mean different than this mean? Is this mean different than this mean? You can just go up there and look. But now we are done with that. And we've just run all three Anovas. It takes us a while. We haven't done descriptives yet or the write-up. I'm only going to do one write-up. And now we... All right, so we have a very simple between subjects design. It's a 2x2 between subjects design. Each participant is only in one of 4 potential cells. So that means they're only in one condition for independent variable 1 and one condition of independent variable 2s. So how do we get the descriptives for independent variable 2? We have to split the data by independent variable 2. And we look at the dependent variable. We make sure we have our mean and standard deviation, standard error clicked. And this will tell us the data for the main effect of independent variable 2. Basically, what I'm looking for are these marginal means, right? I have 2 conditions. I have 2 marginal means. I have 2 conditions. I have 2 marginal means. But you also have standard error and standard deviation and n because sometimes they're useful. Now, I want to run one more descriptive, and I want to get the cell means. Now, cell means are just the means in the interaction, right? This is a 2x2 design, so there are 4 cells. So I'm going to expect 4 means. So I'm going to go ahead and split my data by both of my independent variables and make sure I have my mean, standard deviation, and standard error because you might want to use that to make a graph. You can see it's taken it a second to calculate it, but here are all my cell means, my cell standard errors, and my cell standard deviations. These are what you would use to make your graph of an interaction. These are what you would use to make your graph of this main effect, and these are what you would use to make the graph of this main effect. All right, so now we have a mixed design that I made up just to help you understand descriptives. So we have 2 independent variables. One is a between subjects variable, independent variable 2, because each participant is only in one of the 2 levels. However, if you notice, we also have 2 columns of dependent variables. Dependent variable at control group of independent variable 1 and dependent variable at experimental group of independent variable 1. So we have 2 levels of independent variable 1 and 2 levels of independent variable 2. So it's a 2x2, but it's a mixed design because this is a between subjects variable and this is a within subjects variable. Whenever you see the DV represented more than one time in a row, you know you have a within subjects variable. Now, I want to go ahead and get the data that's the main effect of independent variable 1. So I'm going to click Analysis, Explore Descriptives. And really, this is super easy. I want to find my means and standard deviations. I'm going to go ahead and click standard error and n as well for you. Means and standard deviations for my dependent variable at the control group and my dependent variable at the experimental group. So these means right here represent the mean difference in that main effect. So if I need to make a graph of this main effect, these are the stats I'm going to use. Now, if I click another Explore and click Descriptives, and I want to go ahead and I want to examine the main effect of independent variable 2, you'll probably notice a problem. I do not have an average of the independent variable 1. Now remember, a main effect is ignoring the other independent variable. When we calculated these mean differences, we ignored the other independent variable. Well, here, my dependent variable is tied into my independent variable. So what do? Well, I go back in my data and I say, I need to average these two scores together. I need to average these two scores together. I need to average these two scores together. I need to average these two scores together to just get a pure estimate of my dependent variable that ignores independent variable 1. How do you do that? You double click. You're going to create a new computed variable, average dv. I'm going to click this function button. I'm going to go down to mean, double click, and over here, I'm going to double click and it's going to put in my independent variable 1. I'm going to put a comma. I'm going to double click. It's going to put in my independent variable 2. I'm going to make sure I have parentheses there, and it does. Sometimes it covers those up, so make sure you have 2 parentheses, these little quotation marks around each of your variable names, and a comma. I hit enter, and it gives me the average dependent variable. So now what I can do is go back to my analysis, click exploration, click descriptives. I'm ignoring independent variable 1 with the average dv variable, and I'm going to split it by independent variable 2. I'm going to get my means, standard deviations, and standard errors. And so now this is the data, particularly the means and the standard errors, that I would use to make a graph of the main effect of independent variable 2 on the dependent variable. So now I have my 2 main effects represented, and I want to go ahead and get my cell means. So it's a 2 by 2, so there should be 4 cell means, and you can see all I had to do is split my data by my independent variable and put both of my dependent variable at control group and dependent variable at experimental group into the variables, and you can see that I have, for high at the control group, I have 1 mean. For high at the experimental, I have this mean. For low at the control group, I have a mean. For low at the experimental, I have this mean. What I'm trying to show you here is that sometimes whenever you have a within subjects variable, you're going to have to do some summary calculations to get those main effect descriptive statistics that you need. Now, you can always get the cell means and the cell standard deviations. This one went away for some reason, but now it's back. Okay. But now we have all 3 of our descriptive statistics that we need. The main effect of independent variable 1, 2 means. The main effect of independent variable 2, 2 means. It took off my standard deviation and my standard error, but now we're back. All right. And the cell means, the interaction means, which is 4 cell means in a 2 by 2 experiment. Okay? So those are our means for a mixed design. I'm going to use this same data set to show you what we do to find our descriptives for a completely within subject design. So first thing I need to do is I need to be able to get my marginal means for patient race. Well, if you look here, I do not have a column that is the empathy at just white participants or the empathy at just black participants. I need to create those columns. So how do I do that? I double click, new computed variable, click in my formula, find the mean because I want to average a few answers together. I'm going to go ahead and say this one is empathy white. Okay. And what do I want that to represent? I want it to be the average of empathy white patient and empathy white male and empathy white female patients. So I want to average these 2 together. If you notice, I had to put in my parentheses at the end. It's 2 parentheses, a comma in the middle, and I hit enter. And now I have the average empathy white. And I'm going to go ahead and double click. And now I'm going to create a new computed variable. And this is going to be called empathy black. And I'm going to go ahead and click in the function, find the mean, double click it up there. empathy of black male patients, comma, empathy of black female patients, comma. Hit enter. You can see it calculates it for me. Now I want to get another one, new computed variable. Empathy men. What is that? Well, that's the mean of the white male patient and the mean of the black male patient. Averaging those together. So a main effect of gender ignores race. So when we're developing columns of data, we want one that's just empathy for men ignoring race. Well, that's what we're doing by averaging the two racial men together to get their empathy, right? I'm doing the same thing for empathy women. I'm going to go ahead and click my function. I'm going to scroll down to mean, double click. Empathy white woman, comma, empathy black woman. Make sure that I end it with a parentheses. Hit enter, and it gives me all of my scores here. Okay. So now what I'm going to do is I'm going to go ahead and get my descriptive statistics. First, I'm going to get the descriptives for the main effect of race. So I put in my means. I don't split the data file at all. I put in my two means, my empathy white, my empathy black. Those are my averaged across the genders to see if they're, to see what I'm getting. And I see that empathy for the white patients is 6. Empathy for the black patients is lower. Standard deviation is quite high. Y'all might need standard error to make your graph. They both had 5 observations. But these are my descriptives for the main effect of patient race, ignoring patient gender. That's what a main effect is. So now I'm going to get my explore descriptives, get my descriptives for patient gender while ignoring patient race. It's the same thing. I enter in those 2 columns of data. Make sure I click everything I want, but now I have the mean for empathy for men and the mean empathy for women. I can see that it appears that women have a little bit higher empathy than men. And not, nurses have more empathy for women patients than male patients. That's what we're seeing here. All right, so those are my two main effect data. If I need to make a graph for my main effect of race, I'm going to use these data. If I need to make a graph for my main effect of gender, I'm going to use these data. Now, if I want to get my cell means to get the data for the interaction, that's actually quite easy. I'm going to click exploration descriptives again, and I'm just going to click in all 4 of my original data columns and make sure I click the right options that I would like. And I'm going to keep clicking sample size mean, standard error of the mean, and standard deviation. But you can see now that I have 4 cell means, 1 for empathy at white male patients, 1 for empathy at black male patients, 1 for empathy at white female patients, and 1 for empathy at black female patients. So I want to show you how I come up with the write-ups for you all. So I just found a relatively recent psychological science write-up of an Anova. It says in study 1, they did multiple studies, the Anova on VPS parameter C. So the Anova is the test they ran. VPS parameter C is their DV. Don't worry about what it means. Revealed non-significant main effects. And then it uses this dash and it says session. Then it provides a colon. So that's another way to do it, right? You got some options. Provides the F, the degrees of freedom of the effect, degrees of freedom error, equals 1.50. P equals 0.225. Partial eta squared equals 0.02. Now they put a semicolon there and they put group. They do the same thing. And then they say has hypothesized. Well, that's fine. They hypothesized a group by session interaction. This was significant. And then they report their data right there. They refer to a figure as well. The figure would be the figure that you will make in Excel for your, if you're publishing this, you got to make the figures in Excel. But, you would definitely reference it. And then it shows you how they do post-hoc tests. So they're like post-hoc pairwise tests, because theirs was a within subjects design. You could just write post-hoc test, revealed VPS to be significantly higher after training compared with before training in the alertness training group. You can see it's talking about a complicated relationship that you don't know much about. But what's important here is that they present their T statistic, degrees of freedom, T value, P, 95% confidence interval. This is of the mean difference. So they're doing it differently than I would. With their Cohen's D, I would present the 95% confidence interval of Cohen's D and get rid of that, but not in the other groups. Look at this. P's are greater than 0.547 figure. They refer to the figure again. So, this is a fine Anova write-up. It includes a post-hoc. It includes every single, both main effects and an interaction. It was published in Psych Science, so you can copy it and use it. You can adjust it a little bit. Let me show you how I used it to write up our Anova result. All right, so let's adapt that previous paragraph for our needs. The Anova and happiness scores reveal a large and significant main effective semester, with happiness being higher at the beginning of the semester. F with 1 and now let's enter our statistics. F with 1 and 30 degrees of freedom for the semester main effect, right? 1 and 30 degrees of freedom. That F equals 71.43. The P is less than 0.001, and partial eta squared is 0.70. A large and significant main effective personality, with extroverts being happier than introverts. And again, that you go down, that between subjects effect component of personality, that's your main effective personality. Your degrees of freedom are 1 for personality and 30 for error. So 1 and 30 equals 5.68, comma, your P equals 0.024. Your partial eta squared equals 0.16, and that's where all that data came from. And then finally, a significant semester by personality interaction that's presented here with F with, again, 1 and 30 degrees of freedom, and F of 4.80, your p-value of 0.036, partial eta squared of 14%. We're almost done. It says see figure 1. Figure 1 would be that figure of the interaction, just because we have a significant interaction. If you have a significant main effect and no interaction, make a figure of that significant main effect. If you have all significant main effects and an interaction, you include just the interaction because people can deduce what's going on. And if you only have one main effect and the interaction significant, still use the interaction graph. There's no reason to put all of the graphs in there, but your significance does determine which ones the readers want to see usually. So now I also have the post-hoc data. So post-hoc t-tests indicated that while extroverts were happier than introverts at the start of the semester, and so that's at the beginning extrovert, beginning introvert, we can see that significant t-test. So T with 59.67 degrees of freedom, and that's important. Degrees of freedom aren't always whole numbers, equals 3.24 with a p-value of 0.01. So that's significant. This difference disappeared by the end of the semester, so that's end extroverts and introverts. That T statistic is 0.26. It also has 59.67 degrees of freedom, and its p-value is 0.994. So that's how you do it. That's how you make it work. So now my homework is short. The lecture is long. It's just how it is. When do you use a post-hoc test? Like when? When do you use it for a main effect? When do you use it for an interaction? Make sure your answer is complete. And then what are 2 questions that you want answered in our, it's not a lecture, but our discussion for next class?